Yeah, the snap thing is pretty cool.
Yeah, but
We're talking about.
see how long it is.
Yeah, what I need to do is figure out how I can pull it down.
I said,
Everything
I don't
else
want
is
to
built
do
out.
slits. But I don't.
I just need to figure out the database today.
Yeah, it's just,
Are you-
until you're done.
Is there advanced studio or are you just in the?
Okay, so we were talking about subgroups, normality. The last thing I believe that we discussed was the fact that if you have two left cosets or right cosets, doesn't matter, they're the same size. All right, so let me get off of this.
That's the time.
Y, B, G, and H, B, a subgroup. So this is one way that you can tell if two cosets are the same coset.
Start writing it down.
If and only if X inverse Y is an H. So you might ask yourself, hey, I've got two cosets here. We know the two cosets either have an empty intersection, there's no overlap at all, or they are exactly the same. And here's a way to tell. If and only if X inverse Y is an H. Okay, so suppose XH equals Y. What does this mean? Well, this means that such that there's some element here, call it XH1, that is equal to some element over here, call it YH2. Do I agree with that? Now let's just see, what did I want? X inverse. So let me just start manipulating this. Multiplying on the left by X inverse, now multiply on the right by H2 inverse. This thing right here is an H, right? Because H1 is and H2 is, so H2 inverse is. And so there you go. If the two cosets are the same, this. How about the other direction? Suppose. Now let's suppose that X inverse Y is an element of H. Well, I'm going to use some of the stuff that I already know here. Let me write this down kind of computationally, if you will. Great. Let's multiply by X on the left. So Y is equal to X times H, right? And I don't know much, but I know that this is an element of X capital H. And let me also point out that Y is also in YH. Has to be, right? Because one of the elements of H is
The identity elements.
the identity element. That means that Y is in YH. So Y lives here and it lives here. And what do we know about two cosets? If their intersection isn't empty, then they are the same. And then that's the other direction. Okay. any questions on that? Okay, here's one that I teased you with, before. This is another way to think about what it means for a subgroup to be normal. 419. Okay, so I walk up to you on the street, I give you a subgroup N, even, it's normal in G. If and only if, every left coset is a right coset. Let me write that more precisely. If and only if the left coset in G is the same as right coset other side. If and only if the left coset in G is the same thing as right coset, I'm sorry, the left coset Gn is the same thing as right coset in G. For this, suppose that N is normal in G, and pick your favorite element, little G in here. So implicitly what I mean is G is G, some G and G, and N is some element. Okay, so this is a particular element that lives in this left coset. I'm going to endeavor to show that this thing lives also in right coset. Since N normal in G, you must have that G in G inverse equals N1 in N, right? So what does this mean? Multiply on the right by G inverse. And I obtain that. And what does this mean? This means the Gn is contained in G. Everybody get that? So what have we got so far? Well, what I've got so far is this. Would everybody agree that I could have just started off letting NG be an NG and just sort of done this in reverse? Other containment. The proof is almost the same, it's just the players, the G's are on the other side. So I get G in, this is G. Okay, how about the other? Let's suppose now that for all G and G, Gn is in G. Well, so in this case, let's let N be an N. And G be in G. Little g times little n is in this left coset. But we're assuming this left coset is equal to that right coset, capital T. So what do I know? Right? Because Gn has to be written in this form, something in n times G, and it might be something different from the original. But I do know that n1 is in it. Agree? Multiply on the whatever the side that sits right by G inverse. So n is normal in G. By the way, for this proof, notice I conjugated by putting the G here and the inverse here. Sometimes I've done it the other way, where you lead with the G inverse and then you have the element. It doesn't matter. It's the same result. Okay, any questions? Yes,
What is it? Like, mentally, I was thinking that is the definition of, normal.
some authors do. Some authors will say, the definition of normal is every left coset to right coset. And then they follow it up by using our original definition of normal, right? So, I mean, well, what we've shown here is these two things are equivalent. The original definition I gave you and this definition is the same. Let me give you a notation here with a little bit of a warning. Let's suppose that, let's see, yeah, I'm not considering this is normal here. Let G a even normal subgroup of G. We denote the set of left cosets in G by this notation here. This means set of left cosets of the normal subgroup N and G. All the left cosets. By the way, I could have done this from the point of view of right cosets. From now on, I'll probably pretty much kind of stick to left cosets. Right, so if you see this notation, this right here is just means a set of left cosets. And I'll reserve this for normal. Of course, N could be any subgroup, but I can consider its left cosets. But of course, if it's not normal, some of its left cosets differ from the right coset, perhaps. But here is the big thing about normal. You know, you might have thought, oh, okay, subgroup. Now we've got a normal subgroup. I mean, what's the big deal about this? It's just something that's just cannon fodder for me making up exercises. And the answer is no, because the next theorem is going to tell you why we care, why normal subgroups are better in certain states. Theorem. Here is the magic spoiler. If you look at these set of cosets, it's just a collection of cosets, they themselves form a group if n is one, right? And that is the real important thing here. Let G be a group. And n a normal subgroup of G. For the rest of the statement, the fact that this is normal is incredibly important. The set of left cosets in G. Which forms and group in its own right. Yes,
I may be getting ahead, but can't the identity only be in one of the cosets of the identity of G?
Mhm.
So is there gonna be like a new identity for each?
that's right. It's structurally different. In fact, let me ask you, the set of left cosets forms a group for the binary operation. So Brady brings up an important point here. He said, well, you know, what do you use for the identity? It's one of those cosets, one. The coset that contains the identity of this operation. So,
Say that again? Wait.
or you'll see.
Oh, so yeah, okay.
Now here is a first lesson in algebra. So this might surprise you because math is hard. Probably all your friends say, oh my gosh, you're a math major, look how smart you are. And you are, right? But here is a very important thing in math. Don't do something unless it's easy. I want to take two cosets, two left cosets here, and magically multiply them together somehow and get it to barf out a new coset. Blank times n. That's what a binary operation is. Input two elements of the coset. I need to get a new coset. What is the easiest freaking thing to remember? What do you hope it is? G1, G2, right? And that's the right answer. And that's the first lesson in. If it's math, don't do it unless it's easy, right? This is the way that we form multiplication of cosets. Now, to your point, what is the identity? Under this rule, what is the coset that I can multiply any other coset by? That is correct. I want to write that dramatically. And notice that the coset that acts like the identity is the one that contains the identity, right? Because n or en is the one that has the identity. What is the inverse? What is, notice that G n inverse is equal to G inverse n, assuming this rule works, right? Because G inverse n times G n equals the identity. So it looks like stuff's got the identity. Associativity should just follow from the fact that G is associative, right? Because really, you're doing the same operation here, except it's got this n attached. I'm going to give you a concrete example, then we'll prove this stuff works. Let's let. This is such a great go-to example to start off. Yes.
Let me rewind for 1 second.
Huh?
I'm going back to that G1N, like that notation, right? So those are not like that G1N, that's not a unique, because we can choose any G1 in that.
But you can choose G1 times any n that's in there.
So,
That's right.
oh, so
So you're actually.
the identity one, we use the identity because it's the same as any, this is a really complicated question, but maybe I should do something else, because I don't know how to order.
No, I think you might see this example.
Okay, let me
see if we get lucky.
Okay,
So let's let in. Does anybody remember what there's There was only one normal subgroup of this that wasn't the whole thing or the identity. Anybody remember what it was? And actually, one of the problems in your homework for this week says if you've got a subgroup of index 2, it's always normal. So this one's normal. Let me show you what the cosets are. And actually, it doesn't matter. These are all the same coset. And it's the one consisting of all elements of order 2. Let me just write the one goes to this. Three. Yes.
Can I try asking my question again? If I chose like 1, 2, 3, right, that's in the coset with the identity. It will still work using that definition as an identity.
That is a great freaking question. He said, hey, look, you can use multiplication. Jim says tomato and I say tomato, right? For that coset, I might have chosen E because I'm efficient, and maybe because, I don't know, you want to be more artistic or something, you choose 1, 2, 3 out of here. That's okay. But that's something that needs to be established. Because if I choose one representative for this, and you choose a different, and we get different answers, problem. And that's actually where the normality comes in. That's why your choice and my choice making no difference about this multiplication is exactly the normality that's taken care of for us. You'll see that. But if you see what happens when you multiply, just take it element by element. What happens when you multiply this set times itself? E times all of these repeats the set. 1, 2, 3 times all of these repeats the set, and 1, 3, 2 times all of these repeats the set, right? So this coset times itself is the identity. What happens when you multiply this coset by itself? Well, let's see. 1, 2 times 1, 2 is the identity. 1, 2 times 2, 3 is 1, 2, 3. And then 1, 2 times 1, 3 is 1, 3, 2. Right? So this coset times, or I'm sorry, this coset times itself is this coset, right? So it's sort of like you're putting all the things together and multiplying and see what comes out.
Yeah, I thought that was just a set fraction, but it turns out it was actually something different. Like I thought on the homework, you know, the graduate problem. Is this a case used for the graduate problem on the homework?
Probably.
Yeah.
Yes.
Wait, so is the identity, is the identity,
Yes, it is. But see, the identity, keep in mind, in G mod n, in G mod n for this example here. And yeah, the identity times any set, this set times any other set, just multiply all the elements up, gives a set back for the identity. And and this one times this one gives you this. So this structure is actually isomorphic to C2. Right? This place, if you wrote this additively, this place roll 0, and this place roll 1, 1 plus 1 is 0. Okay. So this is a good example. So what you're actually doing is, when the subgroup is normal, there is a way to take these entire sets and treat them as elements and have this group operation. Right? Yes.
So you said it's isomorphic. Does that, I may remember, does that make it cyclic? If it's like, if it can be isomorphic to C mod two?
Yes,
Is
yes,
that
here,
here for any of these, or just because there's only two of them?
I'd be careful, it's,
Okay.
there's two of them.
Okay.
So let's actually prove this works. So let's prove. Okay, right out of the gate. First. We need. To show. Our binary operation. You gotta show it's a function that is well defined in the first place, because. For example. If I asked to multiply. 1 to n times 1 to n. If I multiply this way, what do I get? The identity in, right? But see, we're all creative humans that might make different choices. Another way that I could write this coset is 2, 3n times 1, 3n. I might pick these two representatives here. And what do I get? Well, in this case, I get 1 goes to 3, 2, 2 goes to 3, 3 goes to 1. But I'm good to go because 1, 2, 3 is still in the same coset as the identity. So we have to show that no matter what choices you make for the representative, whether a pair of 1, 2s, a 2, 3, or 1, 3, or anything you choose, you always get the same answer back. Otherwise, this operation makes no sense at all. It's not even a function, right? This is what I mean by we need to show this well. Well, it's like lots of see what my notation here is. Suppose here my player X, Y, U, V, or G. So here I choose the representative X, and you say, no, I want to choose Y. I choose the representative U. You say, no, I want to choose V. We got to make sure that you and I get the same answers here. Well, need to show X n U n is equal to this is what we need to show, right? So, no. Then what do we know from this? Anybody know? We had a theorem earlier today that said these two cosets were the same, then X inverse Y correct? The cosets being the same means that X inverse Y is an N, correct? Same can be said. B inverse U, bring them in as well. Everybody okay with that? So let's look at this, B inverse Y. Consider oh, this is B inverse Y inverse X BV inverse U. Right, this is the same as this, but I've sort of inserted this BV inverse in between the X. Okay with it? So group theorists love doing this kind of thing. And this is the inverse. And this is in N. Why is it in N? Well, because remember, at the beginning, well, yeah, somebody explain to me, why is this an element of N? I'll give you a hint, look up here.
Yes, inverse.
What's it?
I said V inverse U is in him.
Okay, and what about this one?
Yeah.
This is in N up here, right? This bit is in N, right? So why is the whole shebang in N? Because normally it wouldn't be. But it is here because what do you know about N? It's a normal subgroup. So when I conjugate that, I do this. Everybody agree with that? Okay, so now that I've made that mess here, what we have now is, so what can we conclude now? Since this whole thing is an N and this is an N, so V inverse Y inverse XU is in she is in N. And so from this, is equal to Y. Again, that is the same application as what we had here. The cosets are the same if and only if the inverse of this times this is in. So since this is in N, that means that the coset X U N is equal to the coset Y B N. So it doesn't make a difference if I make my choices of fixing X and U as represented, and you pick Y and B, we get the same answer. So multiplication is well defined. And you just need that normality in this little place here, but it's incredibly important. Now that we know that the operation is well defined, it makes sense, it's a binary operation, it's all downhill from here, right? one, I guess we could have even said that. I mean, it's, now we really need to establish that it's a function first, but now let me observe that it's closed. The product of two left cosets is a new left coset, so we're good to go there. It's associative because if you have x n, y n, let me times z n. Well, by our rule, this is x y n times z n, which is x y z times n. Everybody agree with that? And this is what I meant by, we just kind of get this from the group operation, because the group operation, the original group operation is associative, right? So x, y, n is the same thing as x times, x, y, z is the same thing as x times y, z, right? And this is x n which is x n times y n times z. So, the identity we've already pointed out. Because en times gn is gn, which is gn times en. And for all g and g, gn times g inverse n equals en, which is g inverse n times gn. So g inverse n is gn. And there you go. But like I said, normality of the subgroup is crucial. And actually, it's always good in math to think and make observations here. Everybody saw, it was kind of a subtle place, but everybody saw that I used normal to prove that the operation was well defined, right? I never used normality after that, right? So the only thing that really matters here is just the fact that the operation is actually a well-defined, is well-defined. The rest of it would work anyway. Okay, theorem. So here's a question for you. Just exercise your brain here. One of the things I pointed out is if you have any group, then you've got automatically a couple of normal subgroups. You've got the identity and the whole thing, right? So here is, I won't go through all the details of this, you can guess. E and G are both normal with D. What's that group? G mod G. What's that?
Wait, just because.
That's right, it's the identity. Uh, Let me say it's isomorphic to zero under addition. So, in fact, this group has only one element, because there's only one coset of G and G. Right, because it's the whole group. And so now this thing is a group of one element, so it's the S period. Oh, this one. Very good. G mod, the silly identity is just G itself, because all the cosets are spread out into the separate elements, and it's fairly easy to see with the same group structure. I can give you a theorem. The following conditions are. So I like these kind of theorems, because it allows you to have sort of a tool bag of different ways to think about certain concepts. But E, D, and K, E, C. If you ever see me write TFAE, means the following conditions are equivalent. So these are all one, if and only if two, if and only if three, all the way up to four. Number one. K is normal subgroup of G. Number two, the normalizer in G of K is all G. Oh, wait, I'm not going to prove this theorem. Because this is sort of really a compilation of some of the stuff we've already done, but it's nice to put it in one place. Number two, the left and right cosets coincide. And number four, G mod K is group. You can get all this stuff what we've done before. There's one little missing piece of the puzzle, but I'll leave it to you as a challenge. We know we just proved, in fact, that K is normal G and this quotient is a group. What I didn't prove, which you should probably do because it's kind of a fun little tickler, is show that if this is a group, this happens to be a group, then this is a normal. It has to be a normal. So I didn't show that direction, but it is also. I'm going to give you a silly math. This turns out to be incredibly, even though it might be silly. Proposition 4114. The TV group. And in the normal subgroup, the function I, see, I'll let this pass it in, so be dramatic. So this is sometimes called a projection function. It goes from G to G mod N. And since N is a normal subgroup, then this is the type of group. Given by okay, folks, let's see if we've learned the lesson. Remember, this is a math class, so it's not easy, but I'll do it. So my input is G. My output needs to be some left coset. Which left coset do you think? There you go. Given by I in G is let code set G in. Is a subject homomorphism. And this is sometimes called the canonical projection of G on G mod N. Well, and I want to add something. It means it's on to. Did I answer your question? Maybe I didn't.
Oh, no, didn't you give us a term of that, epimorphism?
Yes, epimorphism, yeah. Anybody want to guess what the kernel of this is? Exactly. The kernel of this homomorphism is all the crap that goes to the identity, which is all the stuff that's in the identity coset, which is just precisely the elements in it. Right. So let's see what this is. Proof. Notice that the high end of G1, G2 is just that coset. And what step do you think I can take from this? I'm trying to show that this thing is a homomorphism.
Would it be G1 and G2S? Or it's like,
Good. And this by definition is in G1, in G2. So this is a homomorphism. Okay, I got that box checked. I want it to be subjective, right? So now suppose X n is an element of G mod n. Well, this is just some random left coset. Notice that I in X equals X n. So I in or on to. And now let's show that the kernel is precisely in. I'm going to do this carefully, because why not? Okay, so I'm going to do this carefully. We said contains both ways. Let's suppose, let's let X be in the kernel of I. What does this mean? Well, this means that I in X. It means this output here has to be the identity element of G mod n, right? Therefore, since these two cosets are the same, X is an n. So we've shown that anything in the kernel of X, or I'm sorry, the kernel of pi, contains n. Now for the other direction, if G and n, then so n contains And so you have quality. Any questions on that? Okay, I'm gonna give you this last proposition for you to think about for next time. And this really characterizes, and this shows an important connection here. So last proposition today. Let T be group. And N T a subgroup. This is an interesting characterization of what it means to be normal. N is a normal subgroup of G. If and only if N is equal to the kernel of phi or some homomorphism phi from G, right? Where H is some other group. But actually, if you prove this, you should prove this, you could actually tell what one of these groups has. But this is an important thing. A normal subgroup is always the kernel of some homomorphism. And the kernel of any homomorphism is always normal. So that's an important connection that we'll explore later. Any questions?
Well, I guess I'll probably head over to office hours to learn when say some homework, because